All right, welcome back to Modeling with Systems of Inequalities. In the first part of the video, we looked at reading through a problem, picking out important information, and creating the system of inequalities. But the reality is there's more to it than that. A system of inequalities, essentially what we're trying to do is figure out a region of points that are potential solutions. We're finding that feasible region. So in this video, what we're going to be looking at is how to create the graph and then also how to actually solve some things. So in this problem, we have C represents the average number of cars a dealership has in its lot. Let S represent the predicted car sales per year. So C is going to be our horizontal axis telling us how many cars are actually on the lot, and S is going to tell us the predicted sales based on time of year or whatever, the number of cars in the lot. The dealership can have up to 90 cars on its lot. So that's going to be important information. I'm going to go ahead and write that as an inequality. Since C is the number of cars, C is less than or equal to 90. In the next part, when the average number of cars on the lot is 60, then at most 480 cars are sold per year. I can try and create a linear inequality for this, but I think it's probably easier if we just start looking at that value. So we're saying that when we have 60 cars in the lot, then we are going to sell, and this is, I'm going to like totally break math conventions here, but it's going to be less than or equal to 480. All right. So our input of C is going to produce 480 or less in terms of car sales. So whenever the average number of cars in the lot increases by 1, the dealership sells up to 2 more cars per year. That sounds like a slope. Oops, got them upside down. An increase of 1 in the horizontal, and that corresponds to up to 2 for the vertical change. So my slope is roughly 2. So I'm going to try and pick out these pieces of information and see if I can get to the correct answer based on that. Start with the first one. C is less than or equal to 90. Immediately I know that graph A will not work because if I go to 90, I should have kind of a boundary set up, and then anything this way should be shaded. But I'm seeing stuff past 90. That's not good for us. We're on a different slide. All right. The second part, 60 and 480, an input of 60 and an output of 480. That seems to correspond okay. Same here and same here. But that other piece of information that at most 480 cars are sold, what that tells us is that we can actually sell less than that. So graph B shows me if I have 60 cars in a lot, I sell at least 480. That doesn't make sense. D shows me pretty much the same thing, that if I have 60 and 480, that's going to be higher than that. So the only one that still works would be C, and it does have a slope of roughly 2 as well. If I add another, let's say 10 cars to the lot, so going from 60 to 70 is a plus 10, then my output is going to change by 20. So C is the correct choice there. So let's take a look at one where they're already going to give us the graphs, and now we want to actually figure out the solution set here. So it says here, a technology store sells tablets and computers. Okay, great. So tablets, based on what's labeled, is our horizontal axis, and then computers would be our vertical axis. In February, they sell exactly 100 tablets and 20 computers. Okay, sounds great. So there's a point there. Interesting. The graph shows two equations related to this problem where T is the total tablet sales and C is the total computer sales. Which of the following combinations could be the technology store's total sales? The key to this problem, there's some numbers that we need to know. First, in January, they're going to sell 300 items, or over 300 items. We don't know what they sold of each, but we know in February they're going to sell 100 tablets and 20 computers. So this graph, here's another piece of information we may quickly glance over and lose. These are the January and February combined sales. So we've got two lines graph right here. One looks like it's got a decreasing graph, another one an increasing graph. What we're trying to figure out is which regions are we going to shade, and then we can pick out the correct point. So January and February total sales combined. We know in January they sold 300 of something. We don't know what. But in February we sold another 100 tablets, so that's 400, and another 20 computers, 420. So they're going to sell more than that because January sells over 300 items. So that line would represent that because our intercepts are 420. So that would be this guy right here. The second piece of information, and I totally missed this here, more of those sales are tablets than computers. So we know that in this region right here, this would indicate that there was more computer sales than tablet sales, just because the vertical is the computers and this is our horizontal, which would be tablets. So based on that, the region, oops, that I'm going to shade for that second piece of information is down in here. So essentially what I'm looking for are any values that are in that region here. So looking at my numbers, if I take 240 and 100, that doesn't quite fit. 360, so these are up by up by 20s, and 180 would fit right in there. And so that one would likely be the one to work. Let me just double check the other ones. 240, 260 is up in this area, and then 120 and 180 is in that area. So again, I know that B would be my correct choice. Okay. Uh, in a standard economic supply and demand graph, consumer surplus is defined as the area greater than or equal to the equilibrium. All right, great. What they're referring to is right in here. They're telling us basically that's our consumer surplus. The system of linear inequalities written and graph below. P represents the price and Q represents the quantity of units that consumers will demand. So this is how much they're going to demand and the price that goes with that. We've got some inequalities listed out, and they're all written right there, but really the key is we want to be able to pick out the feasible region. We've already been told that. The question is asking us the maximum quantity of the tablets that consumers will demand and still have it remain in the consumer surplus area of the graph. So something about demand and in the consumer surplus area of the graph. Okay, but really we're looking for the highest coordinate that still fits in that feasible region. We're not worried about price so much, but just demand. So 200. If I go to 200 on my demand, that's somewhere between the 0 and 500. Just kind of follow it up. It's definitely has some areas that's in the consumer surplus. If I go to 800, again, I'm not worried about price. I just want to see if there's a vertical coordinate, or sorry, a horizontal coordinate that matches up. I go to 800 and I follow it up. There's definitely some region in there. So I know A is too small. If I go to 2800, between 2500 and 3000, little tiny sliver right there. So yes, it's definitely going to fit there. And then 3000, if I go there, I actually hit that point, and I've got to look back at my inequalities because they're all either less than or equal to or greater than or equal to. What that tells me is those lines that form it, the boundary, are going to be part of my solution set and part of that consumer surplus area. And so I think D would work because it is that corner piece for there. And I can actually figure this out and find out that there is a point that corresponds to it by taking 3000 and plugging in here. And I would find that P would end up being 200, which, again, based on the graph, is one of my feasible regions. All right, let's look at one more. So we've got parking lot. It's got 600 square meters available in space. All right, so that's important information. 600 square meters. A car, which is C, so this is going to be our horizontal axis, requires 6 square meters. And a bus, B, which is our vertical axis, requires 30 square meters. Our attendant can only handle 60 vehicles. So what I'm trying to do then is figure out which of these regions would work. So let's start with that. The attendant can only handle 60 vehicles. So that's cars and buses together. That tells me that C plus B has got to be less than or equal to 60. He can handle 60, but no more than that. Based on that inequality, I think I know what region I've got, but let's set up the other one as well. So we've got the number of a car requires 6 square meters. So 6 square meters per car plus the bus requires 30. So 30 square meters per bus, and the area of the parking lot is 600. So we have to be at that amount or less. We can't use more than the space available to us. I want to figure out which of these regions are going to work and which line is which. Let's start with the easier one, the C plus B and 60. Because I've got horizontal and vertical intercepts of 60, I believe it's going to be this line right here. And less than or equal to would indicate it'd be under, but I'm going to test a point just to verify. Plugging in the point 0, 0, that's a true statement. 0 is less than or equal to 60. So I know that part of it is there. So all this area up in here, it's out. We can't use that. So now I'm going to go look at the second one, and I've got that. Well, obviously it's the other line. When I plug in the point 0, 0, I still get a true statement, and so it's going to go in this region here. So my overlap is right there. Now, again, the negative we're not worried about because we're talking about negative quantities of cars and buses. That's just not feasible. We want to see which of these choices then will fit. So if I go to 70 and 2, already I know that I'm not going to work because I'm outside that region horizontally. So that's out. And if I go to 50 and 20, that's in that region immediately said was no good. And going to 20, 30 doesn't quite work. 20 and 10 would be a combination that works. Again, we're taking the same ideas we did in the first video of taking our inequalities, creating an inequality expression, or sorry, an inequality for it, and then looking to see which graphs fit. And now it connects to our section 5, where we're looking for that feasible region and some points that actually work.